Hey everyone, in this video we're going to learn how to graph quadratics in Vertex form. In the last video we practiced writing quadratic functions in Vertex form, so now we're going to use that to help us graph. So our first examples graph the following quadratic equations written in Vertex form by identifying the correct order of transformations that are occurring. Determine the domain and range of each graph. So in this case they've already wrote the function in Vertex form, so we don't have to use completing the square, but we do have to bring back our transformations. So if we look at our first function, y equals quantity x plus 4 squared minus 1, first thing I would do is add 1 to both sides. So y plus 1 equals the quantity x plus 4 squared. So treating this as a transformation, we have a translation of -4, -1. So we can start with the table of values for our parent function, y equals x squared, which will be the parent function for all of these functions. So -2, -1, 0, 1, 2, 4, 1, 0, 1, 4. We can apply the translation of -4, -1, and we can get a new set of points, x, y. So we're going to subtract 4 from every x and 1 from every y. So we have -6, 3. Then we'll have -5, 0. -4, -1. -3, 0. -2, 3. So notice the vertex is -4, -1. Right? So identifying that translation is the same as identifying the vertex. And we can plot these points. So -1, 2, 3, 4, -1, -3, 0, -5, 0 rather, -2, 1, 2, 3, -6, 3. So we can take our points and we can create our parabolic curve. So there we have the graph of y equals x plus 4 quantity squared minus 1. They ask us to find the domain and range here. So the domain is all reals, -infinity to infinity. Range, working from bottom to top, lowest y value is -1, it goes to infinity. If you want to express this as an inequality, it would be y is greater than or equal to -1. Always good to review inequalities in interval notation side by side. Our next function, y equals -1 times x plus 1 quantity squared minus 3. Okay, so same directions, just different function. So I'm going to start by adding 3 to both sides. So y plus 3 equals -1 times x plus 1 squared. That -1's in front of the parent function, so I'm going to divide both sides by it. Okay, so what this tells me is we have both a scaling and a translation. Okay, so the scale factor would be 1, -1, so we have a reflection. And then we're going to follow that up with a translation of -1, -3. Okay, so the vertex here should be at -1, -3, so we'll confirm that to be true. And we're going to apply scaling followed by a translation. So we'll start with the parent function, table of values. Myself a little more room, so -2, -1, 0, 1, 2, 4, 1, 0, 1, 4. So first we'll apply that scaling. Okay, so we'll apply the scaling of 1, -1, so we're going to multiply every x by 1, y by -1. So that's -2, -4, -1, -1, 0, 0, 1, -1, 2, -4. And then we'll follow that up with the translation. So we're going to subtract 1 from every x and 3 from every y. So -3, -7, -2, -4, -1, -3, 0, -4, and 1, -7. So this is also another great opportunity for me to point out how only the translation matters when identifying the vertex in vertex form. because that vertex at 0, 0 in the parent function, after the scaling, was still 0, 0. It was only after the translation that we got the coordinates -1, -3. So now we can plot all the points that we found. So we have -3, -7, -2, -4, -1, -3, 0, -4, 1, -7. So we can connect our points to create the parabolic curve. So there we have the graph of y equals -1 times x plus 1 squared minus 3. The domain is all reals, -infinity to infinity. And the range, working from bottom to top, we're going from -infinity to -3. So this also allows me to point out another example of why vertex form is useful to us. When we graphed quadratics previously, we graphed them in standard form or factor form. And in each of those cases, we always needed at least one x-intercept to draw our graph. Now, with transformations and vertex form, we can graph any quadratic, whether it has x-intercepts or doesn't. Right? This example does not have any x-intercepts, but that didn't create a challenge for us in graphing. We started with the table of values for our parent function, applied the transformations, and got our graph. We didn't need the x-intercepts to do so. Okay, so just a point of emphasis of why we learn another form of quadratics. Now graph the following quadratic equations by rewriting them in vertex form and identifying the correct order of transformations that are occurring. Determine the domain and range of each graph. So now in this case, we're given a function in standard form, so we have to complete the square. So our function is y equals x squared minus 4x plus 9. So we'll start by putting a set of parentheses around x squared minus 4x. So we have y equals x squared minus 4x plus something plus 9 minus something. Okay, so the value that completes the square, so half of -4 is -2, squared is 4. So then we're going to subtract 4 to keep everything balanced. So we have y equals x minus 2 squared plus 5. So moving that 5 to the other side, we have y minus 5 equals x minus 2 squared. So identifying the translation would be 2, 5. So again, we can start with y equals x squared. So that's -2, -1, 0, 1, 2, 4, 1, 0, 1, 4. Then we're going to apply that translation to get our new set of points. So we're going to add 2 to every x, add 5 to every y. So that's 0, 9, 1, 6, 2, 5, 3, 6, and 4, 9. So 2, 5 is the new vertex, so I'll plot that first. 2, 1, 2, 3, 4, 5. And then we have 1, 6, 3, 6. Then we have 0, 9, and 4, 9. Okay, so there are the points, so we can connect them to create our parabola. So there we have the graph of y equals x squared minus 4x plus 9. The domain is all reals, -infinity to infinity. And the range, working from bottom to top, the lowest y value is 5, and it goes to infinity. So this is another example of a quadratic that doesn't have any x-intercepts. So even if we tried to graph it in standard form, unless we just created a table of values and found as many points as we can graph, we wouldn't be able to graph this without vertex form. Next, same directions, we have y equals -x squared plus 6x minus 7. So we'll start by putting a set of parentheses around -x squared plus 6x, or -x squared plus 6x, I should say. So first thing we need to do is factor out the -1. So x squared minus 6x plus something minus 7. Okay, so half of negative 6 is negative 3, squared is 9. But we have to remember to distribute the negative 1. So we're really adding negative 9. So we're subtracting negative 9 to keep everything in balance. So we have y equals negative 1 times x minus 3 squared. Negative 7 plus 9 would be plus 2. So rewriting, we have y minus 2 equals negative 1 times x minus 3 squared. Then we can divide both sides by negative 1, so y minus 2 divided by negative 1 equals x minus 3 squared. So we have both a scaling and a translation. So our scale factors, 1, negative 1, we're multiplying the y values by negative 1, and then we're going to follow that up with a translation of 3, 2. Okay, so start with our parent function. So negative 2, negative 1, 0, 1, 2. So 4, 1, 0, 1, 4. All right, first we'll scale. So we'll multiply every y value by negative 1. So we have negative 2, negative 4, negative 1, negative 1, 0, 0, 1, negative 1, 2, negative 4. Then we can translate these points. So we're going to add 3 to every x and 2 to every y. So that's 1, negative 2, 2, 1, 3, 2, 4, 1, and 5, negative 2. So we're going to plot these points on our graph. So we have 3, 2 as our vertex, so 3, 2. Then we have 2, 1, and 4, 1. So 2, 1, 4, 1. And then we have 1, negative 2, and 5, negative 2. So here we have our graph. Connect our points. So there we have our parabolic curve, domain, all reals, negative infinity. That's not very good. Infinity side, negative infinity to infinity. Our range, working from bottom to top, is negative infinity to 2. Okay. And let's look at the original function, right? We had that a value was negative, so it shouldn't be a surprise that our parabola opens down. Our vertex is a maximum. Right? We completed the square. We identify the scaling and the translation. Apply both, get our points. Last example, y equals 2x squared minus 24x plus 68. Okay, so start by putting a set of parentheses around 2x squared minus 24x. So we have y equals, we need to factor out the 2. So x squared minus 12x plus something plus 68. Okay, so what do we have? Half of negative 12 is negative 6. Squared is 36. We have to think about distributing that 2 out. So it's really adding 72. So we have to subtract 72 to keep everything in balance. So that's y equals 2 times x minus 6 squared minus 4. Okay, so let's rewrite this. So y plus 4 equals 2 times x minus 6 squared. I want to divide that 2, so y plus 4 divided by 2 equals x minus 6 squared. So again, we have a scaling followed by a translation. So our scale factor is 1, 2. And then we're going to follow that up with a translation of 6, negative 4. Right, dividing the y's by 2, so we're multiplying by 2, and then we'll follow that with a translation. Again, we're going to start with the points on our parent function. So negative 2, negative 1, 0, 1, 2, 4, 1, 0, 1, 4. Okay, first up, we're going to scale it. Okay, so we're multiplying every y value by 2. So -2, 8, -1, 2, 0, 0, 1, 2, 2, 8. And then we're going to follow that up with a translation. So we're adding 6 to every x and subtracting 4 from every y. So that's 4, 4. That's 5, -2. 6, -4. 7, -2. And 8, 4. So 6, -4. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4. That's our vertex. And then we have 5, -2. And 7, -2. And then we have 4, 4. 4, 1, 2, 3, 4. And 8, 4. So there we have our points. Connect our points to get our parabolic curve. Domain here is all reals, -infinity to infinity. And our range, working from bottom to top, we have -4 to infinity. When we first looked at this, those numbers seemed quite large, but after rewriting it in vertex form, the numbers worked out nicely. We identified the scale factor, followed by the translation, used both of those to get our graph. So this was another video on graphing quadratics, now focused around vertex form and the idea of completing the square. We've had a lot of practice with completing a square, but more does not hurt. And then we get to take it and actually graph it in these examples. So practice these before you watch the follow-up video here, which is writing a function in vertex form if we're given a graph. Click the Amazon link down below for my algebra workbook so you can practice on your own. Give the video a like, and before you go, click that subscribe button so you can see more videos just like this. Thanks for watching.